I see eu tô mostrando a esse momento de lança não para ninguém e é meio because I should go again for my supplement.
Right. Let's sketch the graph. What does the graph of the velocity time graph look like, Adam? What does the velocity time graph look like? Look at right here. You sure? And the value is what? 6, right? What will the acceleration time graph look like? Yeah. What will the acceleration time graph look like? Dante.
Easy.
Yeah, Dante. What do you think the acceleration graph will look like? Think about the acceleration. Think about how the object accelerated. Uniformly. So the value is G, right? All right. All right. So that was something that we supposed to finish up last week on velocity time graphs, right? Sorry, on terminal velocity. The next thing we just want to run over is Newton's 3 laws. Right? You all know it already, but we are just go it over again, right? Let's just run over Newton's 3 laws. All right, then let's run through these things here. You all have it in your handout. No need to write it, right? Right, Newton's laws, right? Newton's first law, a body continues in a state of rest or in uniform motion, right? In a straight line, unless acted upon by an external force. The law suggests that the body which is at rest requires a resultant force of motion, and if the body is moving, a resultant force is required to increase or decrease the magnitude of the velocity or change its direction. Everything here is form 5 stuff, right? Inertia is what? Inertia is the body's reluctance to motion, right? So the inertia of the body is the resistance to change in motion, and therefore Newton's first law is sometimes called the law of inertia. Hold on. Let's come. Right, it's in the handout if you want to see it, right? Then you can go watch it here. Right? So the inertia of a body is so on and so on. Body of large mass requires a large force to change its motion, and therefore the mass of the body is in measure of inertia. That makes sense? Bigger the object, bigger the inertia. Smaller the object, smaller the inertia. Alright? Mass and weight, it should remember that in mass the scalar, weight is a vector quantity, and it shows you how to prove all of that, right? Newton's second law, right? Newton's second law, they might Still giving the mark here, but remember in C-sec we get F equals ma. Right, now they want to use this rule here, right? The rate of change of momentum. Okay, so Newton's second law is the rate of change of momentum of a body is proportional to the resultant force acting on the body, and it takes place in the direction of the force. Right? Again, everything here you know, and you know that this summarizes the F equals to M. Okay? Again, don't just write F equals to MA. What are you supposed to write? Is it F equals to MA or resultant force equals to mass by acceleration? Resultant force, right? Like what we did here. Newton's second law is the resultant force is equal to mass by acceleration. All right? And the acceleration and the resultant force will one. What we know about them? What we know about the resultant force and the acceleration? They always take place in the same direction, right? So the resultant force here is downwards, and the gravity is acceleration is downwards, right? So they always take place in the same direction. Right, so by definition, 1 Newton is the mass that produces an acceleration of 1 when a mass of 1 kilogram acts on it, right? So you might remember how to do this. If you have F equals to ma, and I ask you to define 1 Newton. 1 Newton is the force when a mass of 1 kg, right, moves at an acceleration of 1 meter per second squared. I'm just not showing all. Oh, look at that, sorry. Right, so if I ask you for a definition, 1 Newton is the force which gives a mass of 1 kilogram and acceleration of 1 meter per second squared. Right, nothing new at all, right? But we're going to use this. You all ever proved linear momentum before? Conservation. We're going to get to prove that here. So we're going to use Newton's 3 laws to prove it. So that's why I'm just going over this for you. Right? Always remember the resultant force and the acceleration are in the same direction. Next, Newton's 3rd law. Right? When object A exerts a force on object B exerts an equal and opposite force on object A. How can I write this as a formula? How can I write Newton's 3rd law as a formula? Object A exerts a force on object B, and object B exerts an equal and opposite force on object A. How can I write that as a formula? How can I write that as a formula?
So,
Object A, yeah.
well, does this have to do with
No, not yet. How we can write Newton's 3rd law as a formula? F of A is equal to what? F of A is equal to F of B, but they take place in opposite directions. F of A is equal to minus F. The forces are equal in magnitude and opposite in direction. Everybody okay with that? Sure. Right, and then you have a few examples there. And then we have linear momentum. Remember this? The linear momentum of a body is defined as the product of its mass and velocity. All right? And then we're going to take a look at the conservation of linear momentum. You gotta remember the law? Total momentum before collision is equal to total momentum. So we have to prove it. All right? So something I want to practice, so let's do me a favor, read this, and we're going to start from right here. Consider an object A of mass m and initial velocity u. Collides with an object B of mass m2 with initial velocity u2. I don't think I use those things. Huh? I think I use u1 and u2 here. Small error here, right? This is u1. This is u2. This is v1 and v2. Take a little read and we're going to do this together. We're going to do the entire proof together. But them ones I don't know.
Take one, but take one. Take one.
All right, sketch that. Sketch that quickly and we're gonna do the proof, right?
Pretty big and I was here without you I care for what you care to very so exciting. I see with the shit out.
Ready? So we're gonna try to prove the conservation of momentum, right?
See, bro.
So we started with Newton's third law.
I see how
Right, so when they collide, right? When these two collide, for the short period of time, when they collide, we know that the force on A is equal to the force on B, right? And they take with opposite direction. Are you okay with that? That's from Newton's third law. From Newton's second law, what do we know? What is the force on A? The force on A will be the mass by the change in velocity, right? That will be V1 minus U1. So the velocity of A changes from U1 to V1. That's okay? All over T. That's Newton's second law. Is equal to minus, same thing for B, mass of B. They all had a mass M, right? Consider 3M. Always a mass of M. Final velocity of P is V2. Final velocity of initial velocity of B is U2 all over T. I'll leave it as an E. Because I don't want to cancel it off, right? Power ampere T's. T will cancel, right? When I multiply this out, I'll get MA V1 minus MA U1. This will be minus MB V2 plus MB U2. Right? Remember, these cancel off, right? I'm moving them across. Anybody get lost? Newton's third law, Newton's second law, and I'm expanding it out. T's will cancel. So I'm bringing all the U's on one side, all the V's on one side. So I'll get ME V1 plus MB V2 is equal to ME U. MAU1 plus MBU2. Are you okay with that? Let's just switch them around. MAU1 plus MBU2 is equal to MAV1 plus MBV2. Right? What this is here? Mass by velocity, right? Mass by velocity for A, mass by velocity for B in this case. So this whole thing here is your total momentum before collision. After they collide, you will have the total momentum after. So what we have there is the conservation momentum. That's why it's that. Now, pull it up now. Right? So the total momentum before it goes after. So you have to be able to prove this using Newton's third law and Newton's second law. Right? Once you remember this minus sign, the rest should be easy. Right? Remember the minus sign and label it properly.
No, just people massive. What do you do about and you guys are also still the man not included.
I can't love it.
Then we don't go like
And when they won level one teacher, they were researcher of that they done, they doing a PhD.
17 contours. But when I was still looking, not good. He started to create it all the time.
Yes, as I know what's it talking. The put down the wall, I think that something. So we show you the graphics. You okay with that? So remember that there's a collision, right? What we have to remember is a few things about collisions. We have to remember a few things about collisions, right? Have different types of collisions. So you have elastic collisions and inelastic. Right? What's the main difference between them? Which one?
And here again, just conserving nothing.
Right? So how do you know which is which? during an elastic collision, the momentum conserved. During an inelastic, momentum is always conserved. Right? So in short, regardless of the type of reaction, momentum always conserved. But kinetic energy is conserved only in an elastic. If it's inelastic, kinetic energy is not conserved. Right? Make a note of that. How you will know if kinetic energy is conserved? How you will know during a collision, kinetic energy is conserved? How you will know that? Right? Find the total kinetic energy before, find the total kinetic energy after, and it should be equal. Right? So all this means is that the total kinetic energy before is equal to the total kinetic energy after. Okay. Yeah. Huh? Yes, downstairs.
So I have a report.
Huh?
I have a report.
Which one? Black? Black.
So what's that one?
Black man just what? But I use that video what going. That's the man.
Say this and then ground.
Yeah.
We start lessons in the same. Yes, sir.
Yes. What it was here?
Yeah, sim. That's sim. So yes, so I said people not to the things.
The map says this. Okay.
Yes, sir. You jump up and become up as well.
When one goes go.
So,
Right here.
it's supposed to be 2 minutes. So, already boxing also. Say, city of our goodness.
Yeah. So the answer that's it.
But yes, it's on how you see.
It's one guy, yes. So yeah, the got the iron, it's iron half together.
Yeah, you take it.
See, next on the person.
Everybody okay with that? Right, and before we wrap up and do a question on this, there's a new term that we're going to look at, and the new term is called impulse. Force by time. So impulse is the force acting per unit time. So the impulse is force by time, or we can say impulse is the change in momentum. Right? So objects try to control this impulse, right? We'll spend some time and look at this, right? Let's do a quick question on this.
Yes.
Soon I'll be
Yes.
What you do?
Let's go on the class.
Alright, let's take a look at this real quick now, just. So state the law of conservation, Nathan, in grade one. Let's do this fast now. State the law of conservation of matter. We can handle that, right? Two objects of masses m1 and m2 respectively traveling in opposite direction collide. The respective velocities of the objects before the collisions are given there. Right? Velocity before collision, velocity after, before, after. Okay? Next, assuming that the law of momentum applies for this collision, calculate the the ratio of the mass of the two objects. All right? So use that information there and see if you can handle part one. What they told you to use again? They told you to use the law of conservation of momentum and find the ratio of the masses. This is more maths than physics, right? Write down the law and make M1 and M2 the subject of the problem. M1 over M2.
Right. Yeah, it's been still.
Right? So use the law of conservation of momentum and the find is remember you don't know the masses, right? So you have to find a ratio of M1 and M2.
Versus the more. Yes.
I know that's what we talk quick now.
Like these exercises.
It's just a whole question. Right, so you started to the momentum before, you got the momentum after. So M1 by U1. Right, plug in the values they give you. And make M1 and M2 the subject, right? Somewhat here. And then one that pass us needs to.
Ano,
I'll see the ring. M1, so it's M1 by 4 plus M2 by minus 3, M1 by minus 1.5, and M2 by 5.5. Right, they still have one more part out there. Right, so all they want is the ratio of M1 to M2. So bringing all the M1s together, M1 by 4 plus M1 by 1.5 is equal to 5.5 M2 plus 3 M2. So when you work this out, you'll get 5.5 M1 is equal to 8.5 M2. Move it across. So move M2 on this side, M1 on M2, move 5.5 on that side. Huh? Right? 8.5 over 5.5. That's okay? That's your ratio, right? Wala ka road, pwede po yung pala 55 naman. That's the ratio.
So 85 in Philippines about.
Next part, calculate the total kinetic energies of the two objects before collisions, given that M1 is that. Hurry up. Two small parts again. Calculate the total kinetic energy of the two objects before the collision and then determine if it elastic. How you'll know if it elastic? FD? Right. If the kinetic energy before equal to the energy after. Okay? Last two parts. And we go back to info. Right, we give it M1 is 8.5. Fine fair. What's M2 by doesn't what's not going? 2 is what? If M1 is 8.5, M2 is 5.5. Right, you can just see that. Find the total kinetic energy between. And then, was it not?
That's crazy. I think it's one of some. I think it was saying. Well, actually, it's something.
It's on right, sugar, right? Anybody you sit down next to you just right, part B, they told us that M1 is 8.5 kilograms. So if you plug it in there, you'll get M2 as 5.5 kilograms. Right, so after you do that, was the collision elastic? Oh wait, no. We had to get the total kinetic energy before and was it elastic? So we're gonna try to find the total kinetic energy before. Are we doing that again? Total kinetic energy before. How are we doing? Half mv squared. So a half m1 v1 squared plus a half m2 v2 squared. So that's a half by 8.5 by 4 squared plus a half by m2 by minus 3 squared. How much again? 10.5? 10.5 joules. And then we have to find the total kinetic after. Online, you all got it conserved or not? No, as after this. As a whole class of circle. What's your understanding concept now? Right, total kinetic energy after, that will be a half by m1 v1 squared plus a half m2 v2 squared. So that's a half by the same thing, 8.5 by minus 1.5 squared plus a half by 5.5 by and V2 was 5.5, right? When you work it out, what you got? Same thing, 10.5. Yeah, 10.5. What I get up? 10.5. So therefore, kinetic energy is conserved. This implies it is. Okay, so this question to make sure you understand what they mean by elastic, right? What again now?
Right. Yes, I know that. So it's not so you agree with that? Well, just stop up though. I'll still yeah, this
But we still, it's just. That's the same thing, I think I know.
no way I'm thinking. Oh, well, actually, this is the problem. You have no more else. Actually, I have no more else. Bro, everybody's mic is the ball. Hey, good on, good on. Yes, I think I'll give up this analysis. I think I'll, like this how I do social company sign it. I'm just not because I'm sure I'm college.
Last thing I'll do. Oh, they get 10.5, yeah, I didn't work it out. Somebody gets it here at 9.
Sorry, Nathan, I don't know Nathan, this is, sorry, Nathan, good answer, see? Yeah.
It doesn't matter if I send them out, it was why I tell.
They done both ways.
So you get the point that.
And we get the point. Yes. We get that point.
You like,
Kita nak kisah kasih tahu.
90.75.
Sorry, what else?
Nathan, is you?
Akin na yung wireless station.
Yeah, why is this Joran?
Isaiah, tell me
No, no, no.
10.5. Isaiah, who listened to the man?
Joran shot the answer. So I said, hey, what? So he don't know this calculator.
Stop, you have to put something.
What happened about? So you know what happened about what the
I ain't even
So
watched
he's on the
That's Isaiah, who tell me that, sir?
So it's just like on your bed. Just show me if you should be together.
Say the original moment.
What do I get for this one? 92.75, alright. Alright, one more thing we're gonna talk about before we wrap up, right? Yes, impulse. Right, so after impulse, we'll be able to focus on circular motions alone next week, right?
Did you just teach him?
No, just go. Right, last thing, impulse. So the impulse of a force is the product of the force and the time in which it acts. Alright? So impulse is forced by time, we just talked about that a little while ago, right? Note that according to Newton's second law, force by time is mv minus mu. Right? mv minus mu. So impulse is also known as the change in momentum. Everybody okay with that? So I think I'll show you that somewhere here. Right? SI unit is what? SI unit is kgms minus 1 or Newton's second. Right. The term impulse is usually associated with a force. Understand? Right? The term impulse is usually associated with a force which acts for a short time. Right? So you have a large force acting for a short time. However, it can also be applied for smaller forces acting for a long time. So consider this here. When an object undergoes a momentum change by an applied force, the applied force may be large for a short time. Interval will produce the same change in momentum. So here's an example. Let's say you were jumping, right? And you jump with your knees bent. What does that do? It reduces the force.
Yeah.
And then what will happen? So remember, when you jump, right? When you jump, and there's going to be a change in momentum. Right. So if there's a change in momentum, then there'll also be a force by the time, right? But remember, Joseph, this force acting on your knees, right? So do you want the force to be large, acting on your knees? No. So if the force has to be small, then this has to be what? So if force is small, time has to be large. So by bending your knee, what will happen? It will increase the time that you will be on the ground in contact with the ground. So it makes that time value larger, but the force smaller on your knees. Right? Since grade 1 packed up already, grade 1, could you explain how a airbag does help in a collision?
That's increased. Is the time chemical.
Right. Yes, help you. Right? When the airbag is deployed, what will happen? It increases the time that you are in contact with car, whereby reducing the force acting on you. Are you okay with that?
Yes.
Right? Could you think of any other examples? Have plenty examples, right? Sometimes it's the other way around as well, where we're a large force for a short time, right? Right, before you pack up and ready to go, just one thing I wanted to talk about on the graph. What? Right? So watch this here. One small thing. If you were to plot, watch this here, because we never did this before, and there are no questions on it. If you plot a graph of momentum versus time, if you plot a graph of momentum versus time, then what does the gradient give you? What does the gradient give you? The gradient gives you force. This is your y, right? This is your y, this is your x, this is your gradient, and this is your y-intercept. All right? Anytime you get a graph, you have to be able to linearize that graph, right? Take the formulas you know and linearize it to find any quantity that they might ask you for. That's okay? All right. So we will stop there. Most important thing is next, we're going to take a look at circular motion next week. Okay? Circular motion has a tendency to come in every 2 years. I think it's stop. Some like small amount,